So when we turn our compact fluorescent light bulb on, which operates by having a type of gas inside of the glass tubes, and then an electric current is sent through it, and so the gas is excited. When we turn that on, we see now not a continuous spectrum of light, but what we see are distinct bands that come out, specific colors, some of them very narrow. If you look at that violet band, it's a very, very narrow band of light at a very specific wavelength. Let's compare the spectrum now to the grow light, which works in a very different way. You see, the grow light works by heating up a piece of wire. It's not exciting a gas, it's just heating something up until it glows hot. And so as a result, it actually creates a completely different kind of spectrum. It produces all wavelengths of light, averaging, or I should say peaking at a specific wavelength. And if you were to see this without the spectroscope, you'd see it was white. But in so doing, it is mirroring what the sun does. The sun just glows very hot and it produces a complete spectrum of light. Notice that there are no distinct bands. There is the complete rainbow. Each color is almost as bright as the next, and there is a continuous spectrum. Again, no distinct bands in this one. Okay, what I'm going to do now is I'm going to try and use the copper chloride one, which you may remember gives a nice bright green color, and you should see that within the spectroscope in the slit there. And hopefully, oh yeah, there we go, there's some lovely bands. So now, you'll notice that there's very intense green, right? There's a high green percentage, but then you'll also notice some lines. Now, there are a lot of lines in this one. Again, a lot of them are in the green, which is why we see green as the predominant color when we burn this particular element. However, you'll notice also distinct bands in the violet spectrum and in the red as well. So what's happening here? Remember that electrons orbit the nucleus in what we call shells or clouds. And there are several clouds, each a little bigger or further out than the previous one. Electrons can move into a higher cloud if given the right amount of energy, say by fire or electricity. In this higher orbit, the electron has more energy, but this isn't very stable. You can think of a ball sitting on top of a hill. Eventually, the electron will fall back down into the lowest possible cloud. And when it does this, it releases all of its excess energy in the form of a photon, a packet of energy. The energy of this photon is exactly equal to the difference in energy between the two electron shells or clouds. And this specific energy corresponds to a specific color of light. Notice that there are many possible ways an electron can change shells. And each has a different energy change and therefore produces a different color photon. On top of this, each element has clouds at unique energies. So, much like a fingerprint, an element's atomic spectra is a unique identifier for that element. All right, so this one is strontium. Again, there's that intense red. This one is cobalt. Last one, calcium. Its unique atomic spectra here having 3 or 4 visible wavelengths. And it's through this property of atomic structure that we're able to produce all the wonderful colors we see in fireworks.